Welcome back to another video. Today we're going to be talking about logarithmic functions. A logarithm, or just a log, is another representation for the value of an exponent. It represents the exponent, or the power to which the base must be raised to produce a given number. So first I'm going to show you how we're going to write things in logarithmic form and how we're going to convert them to exponential form. So in the top corner of my page, I'm going to show you logarithmic form. So you start by writing log. Every log is going to have a base b, which is written as a subscript, in other words, a little letter underneath the log, the argument x, and then equals y. So that is read as log base b of x is equal to y. Now to convert it to exponential form, you're going to, what I like to call a little loop-de-loop or a switcheroo. That's kind of what it looks like. So you start with the base of b, you're going to draw an arrow out, and then you're going to draw an arrow back in. And then to write it in exponential form, you just follow your arrows. So we started with the base, we're going to raise it to the power of y, and then we're going to set it equal to x. Okay, so these two are the same thing, just one of them is written in logarithmic form and the other one is written in exponential form. And we're going to use this for the remainder of this video. So let's start with an example. Log base 10 of 100 is equal to x. So doing your little switcheroo, you start with the base, you draw an arrow out, draw an arrow back in. So that becomes 10 to the power of x is equal to 100. Now, if you think about this, the only possibility for x will be 2, because 10 squared is 100. Okay, so 10 times 10 is 100. Base 10 is the most common logarithm in science and is usually written as log without the 10. So if your logarithm is ever missing the base, you need to assume that it is there, it's just not written, and that the base is 10. And we can see that in the following 6 examples. They don't have a base. So what you can go ahead and do is write a little base of 10 for all of them, and they will all be base 10. Okay. Another thing that some of these problems are missing is the equals x. So I'm going to add that so that we know what we are solving for. Okay. So log base 10 of 100 equals x. So we're going to do our switcheroo, start with the base, out, then back in. That becomes 10 to the power of x equals 100. Okay, we already did this one. X is equal to 2. 10 squared is 100. Okay, let's look at b. So again, with the switcheroo, start with the 10, arrow out, arrow back in. That's 10 to the power of x equals 10. The only possibility would be that x is equal to 1. So 10 to the power of 1 will still be 10. Okay. C. Convert to exponential form, start with the base, arrow out, arrow in. 10 to the power of x equals 1. Okay, so the only power that will ever give you 1 is 0. Let me prove these first 3 to you in the calculator, in case you don't believe me. So the first one was 10 squared. Why is this not working? Okay, my calculator doesn't want to work apparently. Let me restart it. There it goes. Okay, so the first one was 10 squared equals 100. The second one was 10 to the power of 1, which equaled 10, and 10 to the power of 0, which equaled 1. So those were the first 3 problems that we had there. Okay, let's keep going. So the next one, convert it to exponential form, start with the base, do your loop-de-loop. That would be 10 to the power of x equals 0. Now, this one might be a little bit more difficult, so we're going to do it algebraically. Now, if you recall from a few lessons ago, the way to solve for a variable when it's raised to an exponent is to take the natural log of both sides. So that's what we're going to do here. So what that does is bring the power of x to the front so that you're actually able to solve for it, and then you're left with x times the natural log of 10. So again, all it does is take this and bring it to the front. Okay, so 10 goes inside the natural log, and then that's equal to the natural log of 0. Okay, the natural log of a number is just a number. So if you want to get x by itself, you're going to divide it by the natural log of 10, since it's being multiplied by the x, and then we're going to put that into the calculator. Okay, so the natural log of 0 divided by the natural log of 10. And we get undefined. Now, the reason that it's undefined is because the argument is 0, and your argument cannot be 0. So I'm going to make a little note here so you don't forget. Okay, so if your argument is ever 0, that's going to be undefined. And the argument is this part right here. Okay, so that big number next to the log. So not the base, but the number next to the log is called the argument, and that number cannot be 0. And that's why it's undefined. Okay, let's try another one. So we're going to convert it to exponential form by grabbing the base, doing your switcheroo. You got 10 to the power of x is equal to 0.1. Okay, so off the bat, I don't know what this is. So we're going to do the natural log so that we can bring the variable x down to the front. So that'll be x times the natural log of 10 is equal to the natural log of 0.1. Again, to get x by itself, you're going to divide out whatever is being multiplied by x. In this instance, is the natural log of 10. And we're going to put that fraction into the calculator. So the natural log of 0.1 divided by the natural log of 10 is -1. Okay, and you can always double check your work by putting in whatever you had. So we had 10 to the power of x equals 0.1. So we do 10 to the power of -1, we should get 0.1, which we got 1 over 10 because it's in fraction form, but I can convert it to a decimal, and it's 0.1, like I said it would be. Okay, let's come back over here. So x is equal to -1. Okay, last one from this set. Convert it to exponential form. Do your switcheroo starting with the base. Draw an arrow out, draw an arrow in. We have 10 to the power of x equals -10. Okay, I don't know what that is, so we're going to take the natural log of both sides. The x will come to the front of the natural log, and that's equal to the natural log of -10. Okay, you do the same steps as before. Whatever is being multiplied by x, divide it out, and then put that into the calculator. So the natural log of -10 divided by the natural log of +10. Okay, and that's a non-real result, so there is an error there. So does not exist. So that's an error. The reason why is because your argument cannot be negative. So the argument being the one in the parentheses, again, the big number next to the log, not the base, but the big number. So the argument, and write this down so you don't forget it, the argument cannot be negative. Okay, so you have now two restrictions on your argument. So it cannot be 0, okay, and it cannot be negative. So it has to be a positive number in order for you to have a logarithm value. Okay, rewrite each of the following from exponential form to logarithmic form. Now, if you're going to go, so far we've done logarithmic to exponential, so now we're going the other direction. You're going to follow the same loop-de-loop, the same pattern, but before you get started, you're just going to write the word log. You're going to write log, and then you're going to do your loop-de-loop. So you start with the base, you go out, and then you draw an arrow back in. So it's the same pattern, And then wherever you start is you're going to write literally from left to right. So if you started with the 2, that means you're going to have a base of 2. Your next arrow leads you to 32, and your last arrow leads you to the number 5. Okay, so you write them in order. So 2, 32, 5, 2, 32, 5. So you're writing them from left to right, straight across. And then if you want to double check your work, you can do that in the calculator. Okay, let's try the next one. So if you're writing it as a log, you want to start by writing log first. Then you do the loop-de-loop. You start with the 10, draw your arrow out, and then draw it back in. So that's log base 10 of y is equal to x plus 3. Okay. Now we're going to practice going from logarithmic to exponential. Okay, so log of 100 equals 2. Now remember, if you don't have a base, you need to know that there is an imaginary base of 10 there. Okay, so we rewrite this in exponential form. You grab your base, draw an arrow out, draw an arrow back in. You have 10 squared is equal to 100. Okay, we already know that's true. The next one, little switcheroo, start with the base, go out, and then back in. Now, with the base, if you have more than one digit or more than one variable, you're going to want to make sure you put that in parentheses. So this will be 2x in parentheses cubed is equal to x plus 1. Now that's important because the next step will be to distribute the cube, so this becomes 2 cubed x cubed is equal to x plus 1. Okay, and 2 cubed is 8. X cubed stays alone. So your final answer is 8x cubed is equal to x plus 1. Okay. Let's evaluate the following 6 examples. If you notice, these are all missing the equals x. So just go ahead and write that before you get started. Okay, and then we'll get started with letter A. So you're going to do your switcheroo. So log base 3, you start with the base, draw your arrow out, and then draw an arrow back in. We have 3 to the power of x equals 27. To bring the variable down, you're going to take the natural log of both sides. That gives you x times the natural log of 3 is equal to the natural log of 27. You want to get x by itself, so you're going to divide out whatever is being multiplied by x, so you can get it by itself, and then we're going to put this in the calculator. Natural log of 27 divided by the natural log of 3, and we get 3. So x equals 3. Okay, moving on to the next one. Start with the base, out, then in for your switcheroo. So this is 7 to the power of x equals the square root of 7. Take the natural log. This process can get kind of repetitive. X times the natural log of 7 is equal to the natural log of the square root of 7. Divide, and then put it in the calculator. Natural log of the square root of 7 divided by the natural log of 7 is equal to 1/2. Okay, next one. Your little switcheroo, start with the base of 2, come out, then go back in. 2 to the power of x is equal to 1/2. Take the natural log. Bring your x to the front and divide out whatever is being multiplied by x so you can get it by itself, and then type that into the calculator. The natural log of 1/2 divided by the natural log of 2. You get -1. Okay, again, start with the base, switcheroo out, then back in. It gives you the square root of 2 to the power of x equals 4. Take the natural log. Bring the x to the front. Divide out whatever's being multiplied by x so that it cancels, and then put that in the calculator. The natural log of 4 divided by the natural log of the square root of 2, and we get positive 4. Okay, next one, log base negative 5, switcheroo. So negative 5 to the power of x equals 125. Take the natural log. The x comes to the front. Divide out whatever's being multiplied by x. Put it in the calculator. So natural log of 125 divided by the natural log of negative 5. And it's a non-real result, so it does not exist. So D and E stands for does not exist. Now, why does it not exist? That's a good question you're probably asking yourself. The reason why is because of this base. So your base cannot be negative. Okay, so the base has to be greater than 0. Let me write it as just B. So B greater than 0. Okay. It also can't be 0, so it has to be greater than 0. So it can't be 0 and it can't be negative. It has to be a positive number. Okay, let's do the next one. Convert it to an exponential. Doing your switcheroo, we get 1 to the power of x equals 5. Take the natural log. Bring the x to the front of the natural log of 1. Set that equal to the natural log of 5. Divide out. Where did all these things come from? Divided by the natural log of 1. Natural log of 5 divided by the natural log of 1. And that's undefined. And let me explain why it's undefined. So again, it has to do with the base. Your base can also not equal 1. Okay, so it can't be negative, it can be 0, and it cannot be 1. Now the reason that it doesn't work, so let me explain it to you somewhere over here. So the original problem, when you convert it to an exponential form, was 1 to the power of x equals 5, okay? I'm going to put that over here as a refresher. Now, I can try many different exponents for x. So let's say I put 1 cubed. Let's say I do 1 to the power of 7. I could do 1 to the power of 100, 1 to the power of 10,000. I could put any number, okay? And let's test all these in the calculator and see what they give us. Okay, 1 cubed, 1. 1 to the power of 7, 1. 1 to the power of 1 to the power, whoops, I keep pressing the wrong number, of 100, 1. 1 to the power of 10,000, 1. 1 to the power of random numbers that I'm going to just randomly press wherever, is still 1. So regardless of what the exponent is, you will always get 1 if your base is 1. So for that reason, it will never equal 5, which is why this one does not exist. It will never equal 5. There is no power that will ever give you 5. Okay? Let's go on to the next page. All right, so the general idea for the domain and the range. So the domain, if you remember, is the set of the x values. Okay, here the x value represents the argument. And we already said at the beginning that the argument cannot be negative and it cannot be 0. So for that reason, it has to be greater than 0. So I can write the domain as 0 to infinity. So it can be equal to 0 and it can't be negative. Okay, and I'll make a little note here so you don't forget. So the argument cannot, I don't know why my iPad is doing weird things today, cannot be 0 or negative. Okay, and then for the range, it's just going to be all real numbers. So negative infinity to positive infinity. Okay, we're going to do more examples of evaluating. I'm going to set all of these equal to x. We're going to do the loop-de-loop to convert it to exponential form. We have 2 to the power of x equals 256. Take the natural log of both sides. Bring your x to the front of the natural log of 2. Set that equal to the natural log of 256. Divide out whatever is being multiplied by x and then put the fraction in the calculator. Okay, the natural log of 256 divided by the natural log of 2. We get 8. So x equals 8. Okay, another one, convert it to exponential form. Do your loop-de-loop, square root of 3 to the power of x equals 81. Take the natural log. That allows you to bring your power of x to the front. And you got the equals to the natural log of 81. Divide the natural log of 3. Put the fraction in the calculator. Natural log of 81 divided by the natural log of the square root of 3. And that gives you 8 as well. Okay, another one. Convert to exponential form. Do your loop-de-loop. 25 to the power of x equals 125. Take the natural log of both sides. Bring the x to the front. Divide out the natural log of 25 so that you can isolate x and put that in the calculator. Natural log of 125 over the natural log of 25 is equal to 3/2. Okay, another one. Convert to exponential. Start with the base. Do your switcheroo. 49 to the power of x equals square root of 7. Take the natural log of both sides. Bring your variable of x to the front of the natural log of 49. Set that equal to the natural log of the square root of 7. Divide out the natural log of 49. Get x by itself. Type it in the calculator. Natural log of the square root of 7 divided by the natural log of 49. And we get 1/4. Okay. Letter E. Make sure you put this in parentheses. Remember, if it's more than one digit, then do your switcheroo, convert it to exponential form. We got 2 to the times the square root of 2 to the power of x equals 16. Natural log. Bring the x to the front of the natural log of 2 times the square root of 2. Set that equal to the natural log of 16. Divide it out. These cancel. Type it in the calculator. Oops, not my messages. The natural log of 16 over the natural log of 2 times the square root of 2. That gives you 8/3. Okay, and then the last one. So this one is kind of like composition. So I'll do, let's say I do the outside one in baby blue, and then the inside one I'll do it in pink. Okay, so if you remember, composition is where you have f of g of x, and you start with the inside. So we're going to start with g of x, which is log base 2 of 8, set that equal to x. We're going to switcheroo 2 to the power of x equals 8. By looking at that, I do know that x equals 3 just because 2 times 2 times 2 is 8. Now this answer, I'm going to write it, I'm going to substitute it in here. So then my next work will be log base 3, and then that middle part, log base 2 of 8, was equal to 3. And then I'm going to solve it again until I get x. So I'm going to convert this in exponential form. 3 to the power of x equals 3. And the only way to get what you started with is if it's a power of 1. So the final answer is x equals 1. Okay. Now we're going to solve the equations for x. So it's more of the same thing. Log x equals 2. So remember, if it doesn't have a base, you can assume it's base 10. We're going to do the switcheroo, convert it to exponential. We have 10 squared equals x. 10 squared is 100. So x is equal to 100. The next one, switcheroo, start with the 4, go out, then come back in. 4 cubed is x. You can put 4 cubed in your calculator. 4 cubed is 64. So x equals 64. Okay. The next one, switcheroo. We have x to the power of 3/2 is equal to 27. Okay. Now here you can do different things. I'll show you 2 different ways to do it. So if you have an exponent that is a number, to get rid of the exponent, you can take the root of that same number. So if the power is 3/2, we can take the 3/2 root of both sides. So the 3/2 root and the power of 3/2 will cancel out. And then you can type the 3/2 root of 27 in the calculator. So you're going to press this one right here that has a little box outside of the root. Then put 3/2. Inside of that, you're going to put 27 and then press enter. And that gives you 9. Okay, I'm going to show you another way you can do it. And then this will just be your preference. So I'm going to rewrite the problem. X to the power of 3/2 is 27. What you can do instead is multiply both sides by the reciprocal of the exponent. So instead of 3/2, you're going to raise it to the power of 2/3 on both sides. So then 3/2 and 2/3 cancel out, and you're left with x. And then in the calculator, you would do 27 to the power of 2/3. To the power of 2/3, and you still get 9. So it doesn't matter if you do it as the root or you do it as an exponent, okay? But just make sure if you do the power, you're taking the reciprocal. Okay, so either way, you get 9. Okay, last one on this page. Remember to put your argument in parentheses if it's more than one digit or variable. Okay, we're going to convert it to exponential. That gives us x squared. Squared is equal to 81. Okay, when you have the law of exponents, let me give you a little refresher of the law of exponents. Okay, all of my words are crooked. Oops. All right, that's fine. The law of exponents say that if you have one number that has the same base and it's raised to another number, then you are to keep the base and multiply the powers. Okay, so if here we have x squared squared, then we are to keep the base and multiply the powers. So 2 times 2 would be 4. Okay, so we're going to do x to the power of 4 is equal to 81. Okay, so to get rid of the 4, we can take the fourth root. The 4 and the 4 cancel out. Or alternatively, you can also, let me put this in a little bubble so it doesn't mix in with the other stuff. Okay, or you can multiply both sides by the reciprocal. So the reciprocal of 4 would be 1/4. Okay, so let me show you this in the calculator. The fourth root of 81 is 3, or we can do 81 to the power of 1/4, and that still gives you 3. Okay, so now the thing with the powers, if you have a even number root, so I'm talking square root, I'm talking fourth root, sixth root, eighth root, any even number, you're going to need to add the plus or the minus symbol in the front. So this doesn't apply to odd numbers, so it doesn't apply to 3, 5, 7, 9, etc. Only to the even numbers do you need to make sure that you're including the plus or minus symbol, because if you recall, you can have, so if it's an even number, you can have, like let's say this one, for example, I could have 4 negative 3's, or I can have 4 positive 3's, and either way you're going to get positive 81, because these two negatives make a positive, these two negatives make a positive, so the whole thing ends up being positive. So you always have to do plus or minus, because you don't know if the original numbers were all negative or if the original numbers were all positive. So you do the plus or minus just in case. Okay, and that's only for even numbers. All right, moving on to the next page. We're gonna graph 2 to the power of x and log base 2 of x. Now I'm gonna use the coordinate plane they gave me, and I see that it only goes from -2 to +8 on the x side. So on the x side of my column, I'm only gonna go from -2 to +8. So -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, and 8 on both of them. Okay, and then all I'm going to do is graph these in the calculator. So I'm going to start with 2 to the power of x. And this is what the graph looks like. I'm going to pull up the table. And I want to get the x values from -2 to +8. So I'm going to move up a little bit. So you see it's 0.25, 0.5, 1, 2, 4, 8, 16, 32, 64, 128, and 256. Okay, so I'm going to copy those down in the notes. So it was 0.25, 0.5, 1, 2, 4, 8, 16, 32, 64, what was it? Let me look again. 128 and 256. Okay, just making sure. Now we're going to graph log base 2 of x. So I'm going to open a new sheet. Log base 2 of x. Enter. That's what the graph looks like. And we're going to pull up the table. Again, go up to -2. And we're going to go from -2 to 8. So you see the first three values are undefined, but then it goes 0, 1, 1.58, 2, 2.32, 2.58, 2.81 if you round up, and then finally 3. So I'm going to write those over here. So the first three were undefined. And then it went 0, 1, 1.58, 2, 2.32, 2.50, what was it for 6? 2.58, 2.81, and then finally 3. Okay, so I'm just going to pick some of these to plot on our graph. Okay, so negative 2.25 will be like right here. Or in the center. Negative 1 will be at positive 0.5. 0 is at 1. 2, wait, 1 is at 2. 2 is at 4. 3 is at 8. And then after that, I don't have space anymore. But I'm going to connect my points so I can draw the graph. And then this does go on forever, so make sure you're putting arrows on either side of the graph. Okay, now I'm going to do the same thing for the logarithmic function. So it starts after 0, so my first point that I have is 1, 0, 2, 1. I'm going to just do the whole numbers, I'm not going to worry about the decimals. So 4, 2, and then 8, 3. Okay, so this one goes like this. And then we're asked to write the domain, the range, and write the asymptotes of each of these. Okay, so looking at just the pink one, so the domain is it's read from left to right. So we start from the left-hand side and we go towards the right. We see that it goes infinitely to the left and infinitely to the right. So this domain is going to be all real numbers. Now the range, notice that it kind of hovers over 0. So it's going to be from 0 and then goes up to infinity. But it's not going to touch 0. So 0, we're going to have a parentheses instead of a bracket. And as you can see, there is an asymptote. There is a horizontal asymptote that's happening at y equals 0. So this graph will kind of just hover forever like this. Okay, so I can say there's a horizontal asymptote at y equals 0. All right, now let's do the logarithmic function. So from left to right, the domain, it starts at 0 and then it goes out to infinity. And it doesn't touch at 0, so it's going to be 0 with a parentheses and then infinity. For the range, it's going down forever and up forever, so it's going to be all real numbers, negative infinity to positive infinity. And then for the asymptote, this one has a vertical asymptote at x equals 0. I keep pressing the wrong thing. So this graph is going to just kind of hover along 0 forever. So this is a vertical asymptote at x equals 0. Okay, so the final question is, therefore, what is the relationship between the exponential function and the logarithmic function with the same base? Okay, so we can analyze the graph. If you remember from inverses, inverse functions reflect across the line y equals x, which, hold on, I'm trying to make it perfect. Looks like this. So if you were to fold your paper along this diagonal line y equals x, you can see the reflections right here. Graphically, numerically on the table, remember that for inverses, your x and y values switch. So for example, I have the coordinate point 0, 1, and on this side I have 1, 0. So the x and y values switched. 1, 2 becomes 2, 1. 2, 4 became 4, 2. And 3, 8 became 8, 3. So I know there are a lot of decimals in there. These decimals are also in here. They're just not whole numbers for the x values, but we can find them in there. So they will also exist on the other graph. Okay. And then if you remember, another feature of inverse functions is that domain and the range switch. So the old domain becomes the new range. Okay, so these are both all real numbers. And then the range becomes the new domain. So these are both 0 to infinity. And then the asymptotes, you can see that they're the opposite kind. So what's the relationship? So we can say that these two graphs are inverses. So they can say they are inverses. The values in the table switch, oops, that looks ugly. Switch x and y's. And then on the graph, there's a reflection across the line y equals x, and then also the domain and the range switch. So these are all characteristics of inverse functions. So if they're able to reflect across y equals x, if the x and y values switch on the table, and if the domain and the range values switch, then they are inverses of each other. Okay, so exponential functions and logarithmic functions are inverses of each other. Okay, let's go on to the next page. So the laws of logarithms. So we have the multiplication law, the division law, and the power law. Okay, the multiplication law is also written as the product law. The division is written also as the quotient law. Now for the product law, it's basically you have two logs with the same base. So log base b with different arguments, x and y, that are being added together. Okay, so the plus here is important. Okay, so if you have two logs that are being added together, you can condense them. In other words, instead of having two logs, you can have one single log, and you're going to multiply the arguments x times y. Okay. For the quotient law, it's kind of the same thing. You have two logs with the same base, so log base b of x, log base b of y, but this time they're being subtracted. So if you have two logarithms that are being subtracted, you can condense it to one single logarithm and then just divide the arguments x divided by y. Okay, and then the power law, essentially the whatever coefficient you have, whatever is being multiplied in front of the log, you can move it to be to the power, so the exponent of the argument. So it kind of looks like this one. So it's raised to the power of n. Okay, so you can use this to condense. So you can use it to go from two logs to only one log, or you can also use it to expand. So you can go from one log to two logs. So you can go both ways. So they can ask you to either expand or condense. Okay, but the steps you have to follow are these. So let's see steps. Okay, so the first thing you're going to do is take the power law. So you're going to apply power law. Oops, that's ugly. Power law to all logs. Okay, then after that, so step 2, you're going to apply the product law or the quotient law. From left to right. And only one at a time. Okay, so if you start trying to do too many things at the same time, you're going to end up getting it wrong. Now, something that's important here that you may or may not have noticed yet is that all of the bases are the same. So we have base B, base B, base B, base B. So in order to apply the product law and the quotient law, your logs must have the same base. Okay, so let's try some examples. So simplify the following into a single logarithmic form. So we have log 5 plus log 12. So before you get started, you always have to ask yourself, do these have the same base? Okay, so this has base 10, this one has base 10. So remember, if they don't have a base written, it's always going to be base 10. Okay, so what I see there is a plus in the middle of that. So if you see a plus, that's going to be the product law. And just write the word product around it. So what you're going to do is keep the log with the same base. We don't have to write the base of 10 because we already know it's base 10. And you're going to multiply the arguments. So 5 times 12, you can put that in your calculator to reduce it. 5 times 12 is 60. Okay, so your final answer will be log of 60, and that's all you have to do. So if two logs are being added, you multiply the arguments, only if they have the same base. Let's try another one. Remember, you're working from left to right. So the first thing I see is the plus, so I'm going to apply the product law. And these all have base 6, so it's important that you keep checking that. So base 6, 6, and 6, so that's good. So we're going to multiply log base 6 of 10 times 18. Now, we've only done the first two logs. We haven't touched the log base 6 of 5 yet, so just bring that down. Now, for some of you, it might help you also to put your argument in parentheses, so you can do that so you don't get confused. So 10 times 18 is 180. So we'll come back here and do log base 6 of 180 minus log base 6 of 5. Okay, now the next law, I see a minus. So I'm going to apply the quotient law, which means I'm going to divide. So we have log base 6. I'm going to divide the argument 180 divided by 5. Put that in the calculator. 180 divided by 5 is 36. So this simplifies to log base 6 of 36. Okay, let's do another one. Log A plus log B minus log C plus log D. So they don't have any base written, so I can assume that they're all base 10. And we're going to do our laws from left to right. So I see a plus, which means it's going to be the product law. So that means you're going to multiply the arguments A times B. Now, we haven't used the other ones yet, so don't do anything with them. You have to only do one at a time. The next law, I see a minus, so that's going to be the quotient law. So I'm going to divide A times B divided by C. Again, one at a time. We haven't used D yet, so just bring it down. The next law, I see a plus, so I'm going to use the product law again. So that'll be log of A times B divided by C times D. Okay, now to simplify this, you need to learn how to multiply fractions. It's easier if you have them both as whole fractions. So D over 1 would be how you would convert D into a fraction. And then to multiply fractions, you multiply straight across. So you multiply ABD. So AB times D will be ABD. And then C times 1 is just C. Okay, so this log is ABD over C. Okay, let's do the next one. So check the bases. They both have base 4, so that's good. You're ready to go. This one is different than the other ones, though. Notice that this one has a coefficient. So you're going to apply the power law and make it the exponent of the argument. So we're going to rewrite this as log base 4 of x squared minus log base 4 of x plus 3. Okay. The next law that I can apply is the quotient law. I know that because they're being subtracted. And the quotient law tells me to divide the arguments. Okay, so we can leave this as the final answer. log base 4 of x squared over x plus 3. Okay, next example, write as a single logarithm. So I see some coefficients there. Well, first let's check the bases. They don't have any, so they're both going to be base 10. I have a coefficient. Again, if it helps to put your argument in parentheses, I recommend that you do that. Move the coefficient using the power law on both of them. So you can do both of them at the same time. Okay, so that's the power law. So this will be log of x cubed plus log of the square root of x minus 1 squared. Okay, and then you can simplify this. So the square root cancels out the square. So we can rewrite this as log x cubed plus log of x minus 1. Okay, now the next law we can use, there's a plus, so that's going to be the product law. So I'm going to multiply the arguments, log of x cubed multiplied by x minus 1. Okay, I have to distribute that x cubed. So the final answer, x cubed times x is x to the power of 4, and x cubed times negative 1 is negative x cubed. Okay, next one. I see some coefficients. Start by putting your arguments in parentheses, and then we'll apply the power law. So we have a coefficient of 1/2 that's going to go to the back, as well as the 4. Now you're not going to take the negative in front, you're only going to take the coefficient, because that negative is not attached to the 4. That negative is to tell you to apply the quotient law. Okay, so I'm going to rewrite this as log base 2, and they're both base 2, so make sure you're always checking that they're the same base, of x to the power of 1/2 minus log base 2 of the square root of y plus 3 all to the power of 4. Okay, now the minus, like I said earlier, is going to tell you to apply the quotient law. So I'm going to divide log base 2 of x to the power of 1/2 over the square root of y plus 3 to the power of 4. Okay. Now that x to the power of 1/2, so you might not remember when I taught you this, so I'm going to put it here to the side. If you have, let's say this is a and b, you can rewrite a power that is a fraction by using a root. So the denominator will go outside of the root, and then the numerator goes as the power inside of the root. Okay, so on this one, when we have x to the power of 1/2, you're going to do the square root of x to the power of 1. Okay, you don't usually see the 2 in front of the square root because that's the most common root. So it's the same thing. Log base 10 is the same thing as log. Okay, so the square root is the same thing as just the square root. So you don't really need the 2. The 2 is imaginary. It's technically there, but you might not know that it's there if no one ever taught you that there is a square there. But anyways, all this to say that I'm going to simplify this as just the square root of x, because we don't need the 2. And then also x to the power of 1 is just x. Okay, so this will simplify to log base 2 of the square root of x over the square root of y plus 3 all to the power of 4. Okay. Let's go to the next page. So now we're going to evaluate. Okay, I'm going to apply the product law. Put your argument in parentheses. Move all of the coefficients to behind the arguments. So this is all power law. These are all base 3. Okay, so you want to check the bases and make sure that they're good. So log base 3 of 6 cubed minus log base 3 of 2 to the power of 4 plus log base 3 of 4 to the power of 1/2. Okay, So I can simplify all of these in the calculator. 6 cubed is 216 minus log base 3, 2 to the power of 4 is 16, and then 4 to the power of 1/2 is 2. Okay, now we can go left to right applying one law at a time. So I see a minus, that's going to be the quotient law, telling me to divide the arguments. So 216 divided by 16, and we haven't used the other one yet, so just bring it down. Okay. The next law is the product law because of the plus. So we're going to multiply. We can figure out what 216 divided by 16 is. It is 27 over 2. And you're going to multiply that by 2. Okay. So the answer times 2 is 27. So log base 3 of 27. All right, so this one is different. The instructions say evaluate. When it says evaluate, your final answer should be a number. The previous one said simplify and write as a single logarithm. Write as a single logarithm. So every answer had only one log in it. Okay, so if it says write as a single log, you should have a log in your answer. If it says evaluate, you need to have only one number. So now we're going to write log base 3 of 27 in the calculator to get the number. So it equals 3. Okay, so if it says evaluate, your final answer should be a number. Okay, moving on to the next one. So we have coefficients that we're going to apply the power law to. So we're going to move all of these to the back using the power law. So we have log base 5 of the 4th root of 125 to the power of 2/3 minus log base 2 of the square root of 32 to the power of 3. Let me move this over. And then plus log base 3 of 81 to the power of 4, all to the power of 1/2. Okay, now I don't know if you noticed while I was writing this, but these are all different bases. We have 5, 2, and 3. So you might be thinking to yourself, so now what? What am I supposed to do if they have different bases? So it's actually easy. All you're going to do is type it into the calculator. Now, if you're detail oriented and you can do this all at one time, good for you. But from my experience, you guys are not that not that good at typing things, especially when they're very long like this. So what we're going to do is break it up. So I'm going to do this piece first, then this piece, and then finally this piece, and then we'll add them all up. Okay, so the first one is log base 5 of the 4th root of 125. Whoops. 4th root of 125, and this is all to the power of 2/3. So that gives me 1/2. So for this first part, I have 1/2. Okay. Then the next part, I have negative log of base 2 of the square root of 32, all cubed. And that gives me negative 15 over 2. Okay. Then the next one is positive log base 3 of 81 to the power of 4, and then all of that to the power of 1/2. Okay, and that gives you 8, positive 8. So now all we're going to do is put all this back in the calculator. So 1/2 minus 15 over 2 plus 8 is equal to positive 1. So the final answer is just 1. Okay. Now we're going to be solving equations. So far we have just been writing as a single logarithm, rewriting from exponential to logarithmic function, and all of that is to lead us to actually solving logarithms. So there are two general forms. You can have log base c of L equals log base c of R. So you can if you can simplify both sides to a single logarithm with the same base, then you can equate the contents of the logarithms. So if you have two logarithms of the same base, so notice that we have log base c and log base c, so two logs of the same base that are equal to each other, then all you need to do, basically they can cancel out, and all you have is the left argument equals the right argument. So all you need to do is equate the contents of the logarithms. Okay. The other one is log base c of L equals m. So if you have a logarithm that's equal to a numerical value, you're going to rewrite it in exponential form. So if it's equal to a number, you're going to rewrite it in exponential form. So this is what we've been doing at the beginning. Grab the base, arrow out, arrow in, so that's c to the power of m equals L. So that's your little loop-de-loop. So you have two options here. Either you have two logs equal to each other, or you have one log equal to a number. And then you're going to do different things depending on which form you have. When you're giving your final solutions, you must be aware of your restrictions. Now, if you remember from the first page, the restrictions are that your argument cannot be negative or 0. So your argument can only be positive. So we're going to double check all of our answers to make sure that the argument is going to stay positive. Okay, so let's start with letter A. Solve each of the following and check your solution. So we have log base 2 of x equals log base 2 of x plus 2 equals 3. So before you apply either of these two cases, either case 1 or case 2, you have to condense each side so that there's only one logarithm. So on this side of the equal sign, I have two logs. So I need to condense that into one log. I'm going to be using the law of logarithms. Okay, so that minus, we're going to use the quotient law. So I'm going to divide the arguments x divided by x plus 2 equals 3. And I did check that the bases were the same. They're both 2. Okay, so now I'm going to look at my options. So does it look like two logs equal to each other or one log equal to a number? It looks to me like number 2 because I have one log equal to a number. So that means I'm going to have to rewrite it in exponential form using my little loop-de-loop. So I start with the base, arrow out, then arrow back in. So this is 2 cubed is equal to x over x plus 2. 2 cubed is 8. Okay. If you recall, to get rid of a fraction, what you're going to do is multiply both sides by the denominator. And that cancels this out. Now on this side, you're going to have to distribute the 8. So you have 8x plus 16 equals x. We're trying to get x by itself. Right now we have an x on either side. So I'm going to try to get the x's on the same side. So I can subtract 8x. So I have 16 equals negative 7x. And if I divide by negative 7, then x would be equal to negative 16 over 7. Okay, now don't box on any of your answers until you check your argument, because the argument cannot be negative or 0. So what you're going to do, if this is x, you're going to plug it in this argument and in this argument. Okay, so if I plug x into this argument, that gives me log base 2 of negative 16 over 7. That is not possible because we just said the argument has to be positive. Okay, so that's not going to work. Let's test the other argument. Okay, so this gives us log base 2 of negative 16 over 7 plus 2. Okay, so what we can do is type this in the calculator and see if it's positive or negative. So negative 16 over 7 plus 2. That gives me a negative fraction. So both of my arguments ended up being negative if I plug this into this x or that x. So for that reason, this is actually not going to be a solution. And since there aren't any other solutions, letter A actually has no solution. Okay, so sometimes you can get a value for x, but that will not necessarily be your answer. Okay, so you always make sure that you double check your arguments. And move all of this over. Okay, let's do letter B. So first thing you're going to do again is condense. So you don't want to have two logs on one side. So this is the equals, and notice I have two separate logs here. So I'm going to condense them using the law of logarithms. So I see a plus, which tells me that's the product law. These are both base 5, so that's good. So now I know that there's something wrong with my Apple Pen, I think. I'm gonna multiply the arguments and put them in parentheses because we have two binomials here. Okay, so we have log base 5 of 2x minus 1 times x minus 2. To multiply two binomials, we're going to use the box method. You can do FOIL if you prefer that. 2x times x is 2x squared. X times negative 1 is negative x. 2x times negative 2 is negative 4x. And negative 2 times negative 1 is positive 2. So I'm going to come back and write this here. So log base 5 of 2x squared, my like terms being negative 4x and negative x equals negative 5x, and then positive 2, and that equals 1. So after you condense to one single logarithm, you're going to compare, does it look like this one or does it look like that one? Mine is equal to a number. This one is equal to a number, so I'm going to assume it's case number 2, so I'm going to rewrite it in exponential form. So I start with the base, do your loop-de-loop, arrow out, arrow back in. We have 5 to the power of 1 equals 2x squared minus 5x plus 2. What is 5 to the power of 1? Anything to the power of 1 will always be what you started with. So it's still 5. So I don't really need to put the power of 1 right there. Okay, now this is a quadratic. To solve for quadratics, you use X method, but before you use X method, you need to have your quadratic equal to 0. So I'm going to subtract 5 from both sides so that this can be equal to 0. We have 2x squared minus 5x minus 3. Now I'm going to do X method. So on the top, remember you have A times C. On the bottom, you have B. Okay, A times C, that's 2 times negative 3 is negative 6. Your B is negative 5. And when your A is not 1, you need to put the A on the bottom of your fractions on the side. Okay, so what two numbers multiply to negative 6 and add up to negative 5? Those numbers would be 1 and negative 6. And then you got to analyze the fractions. So they simplify. 1/2 doesn't, but negative 6 over 3 does. So that equals negative 3 over x. So we're going to come back over here. 0 equals 2x plus 1 times x minus 3. Now, how do you get the x's? You're going to separate the factors. So 2x plus 1, set them each equal to 0. X minus 3 equals 0. Okay, so 2x plus 1 equals 0. You're going to subtract 1, then divide by 2. So on this side, x is equal to negative 1/2. Hold on, I'm running out of space. I start moving some things over. I'm going to move this here. I'll move this one up here. I'll put this one over here. Okay, now for the other one, we had x minus 3 equals 0. You add 3 and x equals 3. Now remember, before you box in any of your answers, you need to double check that the argument is not going to be negative. So I'm going to type the negative 1/2 in here and also in here. So we're going to type 2 times negative 1/2 minus 1. 2 times negative 1/2 minus 1. That gives a negative 2. And then the other argument was x minus 2. So we do 2, sorry, if we do negative 1/2 minus 2, it's going to be negative 5 over 2. So both of those are going to give you a negative argument if you do negative 1/2. So I'm not going to select negative 1/2 as the answer. Okay, now let's try to insert positive 3. So I can do positive 3 in here. I can do that on the screen. So 2 times 3 minus 1. 2 times 3 is 6, minus 1 is 5. 5 is a positive number, so that one checks out. Now let's try x minus 2. 3 minus 2 is 1. That is a positive number, so it checks out. Okay, so because both of them give you a positive argument, x equals 3 will be the solution. So not negative 1/2, just the 3. Okay, let's try C. So again, look at both sides of the equal sign. This one only has 1, so that one is good. But this one has 2. So before we proceed, we need to condense the left side to a single logarithm. So I see a plus symbol, so I'm going to apply the product law. So I'm going to multiply x minus 6 times x minus 2. And that's equal to log of 5. And these are all base 10 because it's not written there. So we are good to go on that end. Okay, so I'm going to use the box method again to multiply my binomials of x minus 6 and x minus 2. Okay, we got x squared, negative 6x, negative 2x, and positive 12, and then the like terms. So this will be log of x squared minus 8x plus 12 is equal to log of 5. Okay, so look at your options. So do you have two logs equal to each other or a log equal to a number? I see a log on the left and I see a log on the right. So I know that's going to be case 1. So if they have the same base, I can just cancel out the logs and then I'm just going to write the arguments equal to each other. Okay. And then this will kind of just solve like last time where it's a quadratic, so you need to make sure it equals 0. So I'm going to subtract the 5 on both sides. So 12 minus 5 is 7. And then we can do x method on the side. Okay, so a times c, 1 times 7, b is negative 8, and then a is 1. So we don't have to put a number there. So what two numbers multiply to 7 but add up to positive 1? Sorry, what two numbers multiply to positive 7 but add up to negative 8? Those two numbers are negative 1 and negative 7. So I'm going to rewrite these as x minus 1 times x minus 7 equals 0. And then to solve, we're going to set each factor equal to 0. So x minus 1 equals 0 will give you positive 1, and x minus 7 equals 0 gives you positive 7. Okay? But we need to plug both of these in to make sure that they're going to work. So let's start with 1. 1 minus 6 is negative 5, so that does not work. Let's try the 1 in here. 1 minus 2 is negative 1. Okay, so this one gives you negative 5. This one gives you negative 1. You cannot have a negative argument, so x equals 1 is not a solution. Let's try positive 7. Okay, 7 minus 6 is 1. That's good because it's positive. Let's try x minus 2. You have 7 minus 2, it's 5. 5 is a positive number, so that one is good. So x equals 7 will be the only solution for this problem. Okay, so it's important that you check your answers. Let's do the last one. We have to condense the left-hand side. I see a minus, so I'm going to apply the quotient law. These are all base 3. So we have log base 3 of 2x plus 4 over x minus 1 is equal to log base 3 of 8. They're both log base 3 on the left and the right, so you can get rid of that and then just set the arguments equal to each other. Okay, and then you're going to just use algebra. So remember, to get rid of a fraction, you're going to want to multiply both sides by the denominator. So these two cancel out, and then you do have to distribute this over here. So this will become 2x plus 4 is equal to 8x minus 8. Okay, you're going to want to get the x's on the same side, so I can subtract 2x on each side. That gives me 4 equals 6x minus 8. Then I can add 8 on both sides. 8 plus 4 is 12. That's equal to 6x. And then if I divide by 6 on both sides, 12 divided by 6 is 2. Okay, let's see if that 2 will work. So I'm going to put 2 in here. 2 times 2 plus 4. 2 times 2 is 4, and 4 plus 4 is 8. 8 is a positive number, so that one is good. Let's try x minus 1. 2 minus 1 is positive 1. That's a positive number. So x equals 2 will be the final answer. Let me write it up here. Okay, so that one is perfect. Okay, let's go on to the last page. We're going to try some word problems. An earthquake rated at 3.5 on the Richter scale is felt by many people, and an earthquake rated at 4.5 may cause local damage. The Richter scale magnitude reading M is given by M equals log base 10 of x, where x represents the amplitude of the seismic wave causing ground motion. How many times greater is the amplitude of an earthquake that measures 4.5 on the Richter scale than on the one that measures 3.5? Okay, so there are two different earthquakes happening, and there's different variables. So there's two different variables happening. So they tell you the Richter scale magnitude reading is M, and M is this equation. Then they tell you that X represents the amplitude of the seismic wave. Okay, then they tell you how many times greater is the amplitude of an earthquake that measures 4.5 on the Richter scale. So an earthquake that measures 4.5 on the Richter scale. The orange one also said Richter scale reading. So I'm going to assume that is still the letter M because it says 4.5 on the Richter scale. And then there's another earthquake that's measuring 3.5 on the Richter scale. Okay, so I'm going to write the formula. M equals log base 10 of x. Now, we're used to having the number be on the right-hand side, so I can just rewrite this so that the M is on the right. So it's the same thing, just it's easier for us. Okay. And then, so X is what we're going to be solving for. So we have two separate earthquakes. So we have one where the M, the Richter scale magnitude reading is 4.5. So M is 4.5. And then I have another one where the Richter scale reading is 3.5. And we're trying to find how many times greater is the amplitude. So we're finding the amplitude, which is the letter X. Okay, so to solve for this, we have one log that's equal to one number, which means you're going to rewrite it in exponential form. So that gives you 10 to the power of 4.5 equals x. And on this one, 10 to the power of 3.5 equals x. Now the question is asking you how many times greater. Now the operation that represents how many times greater is division. So you need to divide the bigger one, which is 10 to the power of 4.5, by the smaller one. So we're going to divide that in the calculator. 10 to the power of 4.5 divided by 10 to the power of 3.5, and that value is 10. So the amplitude is 10 times greater. Okay. So even though the numbers are not that far apart, it did specify that one is just felt by the people and the other one causes local damage. So the one that causes local damage, the earthquake is 10 times stronger. Okay, last problem. A spacecraft can attain a stable orbit 300 kilometers above the Earth. If it reaches a velocity of 7.7 kilometers per second, the formula for a rocket's maximum velocity v in kilometers per second is v equals negative 0.0098 t plus c times the natural log of r. The booster rocket fires for t seconds and the velocity of the exhaust is c kilometers per second. The ratio of the mass of the rocket filled with fuel to its mass without fuel is r. Suppose a rocket used to propel a spacecraft has a mass ratio of 25, an exhaust velocity of 2.8 kilometers per second, and a firing time of 100 seconds. Can the spacecraft obtain a stable orbit 300 kilometers above the Earth? Okay, so there are a lot of different variables happening, so we're going to go one by one. So the first thing they say, let's see, rocket's maximum velocity v. Okay, now this might seem like a tedious, unnecessary step, but when there's a lot of variables, their goal is to confuse you. So you're going to want to organize all of your variables to avoid this happening. So v is the max velocity. Okay, the next letter that we see is time. Little t is time in seconds. The next variable, the velocity of the exhaust, is c. Okay, so c will be the velocity. We can just say exhaust velocity. Let's see. The ratio of the mass of the rocket filled with fuel, blah blah blah, is r. So r is the mass ratio of the mass. Okay, and then we can get into the actual numbers. So suppose a rocket has a mass ratio of 25. Okay, mass ratio is r, so r is 25. Exhaust velocity is c, so c is 2.8. Firing time of 100 seconds, so t is 100. And then the one thing I haven't highlighted yet is the actual equation. So the equation is v equals negative 0.0098 t plus c times the natural log of r. And it wants to know, can the spacecraft obtain a stable orbit above 300 kilometers above Earth? So the first sentence actually said a spacecraft can obtain a stable orbit 300 kilometers above Earth if it reaches a velocity of 7.7. So we're going to find the velocity, and then if it reaches 7.7, or if it goes above and beyond 7.7, then we can say yes, it does. If it's below 7.7, then it will not reach a stable orbit. Okay, so let's plug in all the numbers we have. So v equals negative 0.0098 times t, which is 100 seconds. I'm running out of space. And move this over. Plus c, which is 2.8 times the natural log of r, which is 25. Okay, then we can just go and type this straight into the calculator. So negative 0.0098 times 100 plus 2.8 times the natural log of 25. That gives you 8.03 if you round. So the velocity is 8.03, and the velocity was being measured in kilometers per second. Okay, so now for the answer. Can the spacecraft obtain a stable orbit? So remember, the condition was if it reaches 7.7. Ours reached 8.03. That's well above. So let's write the answer. So yes, it obtains a stable orbit because 8.03 kilometers per second is greater than the minimum velocity needed of 7.7 kilometers per second. Okay, and so that's it. So this was a really long lesson. It went over a lot of different things involving logarithmic functions. If you guys have any questions for me, leave them in the comments, and I'll see you in the next video. Goodbye.